Kiana may have issues on Zoom. Okay, I guess it's, well, 1 minute to start, or less than a minute. Does anybody have any questions about anything before we start? Yeah, I hope so. I think I will. Okay, well, in that case, I do want to jump into it because I want to finish this. So we left off last time, we're talking about different types of concentration units. And you should be familiar with molarity, but the other ones, molality and mole fraction, we'll use coming up with colligative properties. So this is just the numbers. So to this problem, the solution is prepared by dissolving 17.2 grams ethylene glycol in a half a kilogram of water. The final volume is 515 milliliters. What is the concentration of the solution in these units? So ethylene glycol, so I think it's 62. So 2 times 12 for carbon plus 6 plus 32 for 2 times oxygen. So 24 plus 6 is 30 is 62. 62 grams per mole. So 17.2 grams ethylene glycol. Ethylene glycol times mole, 262 grams. That is, let's cheat. 0.277 moles ethylene glycol. I'm just going e.g. ethylene glycol. So molarity is moles per liter. So it's going to be 0.277 moles and liter. It's does it bother you if I just put 0.515 liters? 515 milliliters is 0.515 liters. And that then becomes 0.538 molar. So then compare this to molality. It's going to be moles ethylene glycol 0.277 moles over 0.5 kilograms. And so what is that going to be? It's going to be equal to 0.554. And we use the term molal. So it's 0.538 molar, 0.554 molal. So you can see they're close, but they're slightly different. So ever so slightly different. So does anybody have any questions up to this point? Okay, so percent by mass. So mass 17.2 grams ethylene glycol over the total mass, which is 17.2 plus 500 grams. So, and you do that, well, I guess times 100%. Times 100%. And if you do that, you get 3.33% ethylene glycol. But I'm sure people are okay with mass, well, by concentrations by mass percent, because, you know, it's, we do that colloquially as well. And I use the body fat example. Then mole fraction, it's going to be moles ethylene glycol over total moles. So our moles ethylene glycol is 0.277 moles all over 0.277 plus water 500 grams divided by 18 grams per mole. So this here is the moles of water. And the mole fraction then becomes 0.00989. And then the mole percent, it's just the mole fraction times 100%, 0.00989. Oh, actually, no, I got no zeros. Just 0.989%. Yes, I can multiply by 100 without a calculator. So does anyone have any quick questions on how to solve these? Usually it's pretty straightforward. Let's see if you can follow here. So you have a solution. It is prepared by adding 50.4 grams of sucrose to 0.332 kilograms of water. Volume is 355 milliliters. What's the molarity? I'll give you guys some. Sucrose is 342 grams per mole, but I'll go ahead and do 50.4. This is going to be 0.15 moles of sucrose, 147, but nah. And the moles of water, 32 divided by 18. I better put more units on here. 147. $18. But I went ahead and put it's 18.4 moles of water. That I just 332 divided by 18. Yeah, 332. I'm trying to do some of the work for you. Yeah, 18.4. 18.4 was the Z bar and the 4. Trying to give you some hints. Yeah, 50.4 divided by 50.4 plus 332. You can put the parentheses on the bottom if you're doing it in the calculator. So let's just, do you guys need more time or okay, I see people are still playing with their phones. Okay. Yeah, I got my phone. Okay, this is my phone. It's amazing how much you can't smell wearing these masks. I don't know about you guys, but like, smell is important to me. I don't think I've had COVID. I'd hate to lose my sense of smell. I'll kind of go ahead and jump ahead. That's the first two answers. Did anyone not get those? It's okay if you don't. I'm just trying to. And this is really just putting, at this point in time, just putting your numbers in the calculator properly, which is actually is a skill. That's here. Fine. So you actually got okay. Sorry, I'm looking over your shoulder. Okay, looks like everyone's. It looks like everyone's following. Anybody have any questions with this? So, but this is pretty much straightforward. Okay, and the next thing we're talking about are colligative properties. And colligative properties, these are properties that depend on the number of particles. And so they're vapor pressure depression, freezing point depression, boiling point elevation, and osmotic pressure. So, and we're at 14. Okay. So we'll start out with Raoult's law. So Raoult's law deals with vapor pressure, and the P in this case is the vapor pressure. So the vapor pressure of the solution is the mole fraction of the solvent, and the mole fraction specifically by the number of particles. So, and then the whatever starting vapor pressure of the pure solvents. So, for instance, calculate the vapor pressure at 25 degrees Celsius for a solution that's 99.5 grams of sucrose, 300 milliliters of water, and the vapor pressure 25 degrees Celsius. Pure water is 23.8 torr. So what this means, we have 300 grams of water. So we need to have a mole fraction of water. So it's the mole fraction. So X is the mole fraction of water. It's the moles of water, 300 grams divided by 18 grams per mole, all over the total moles, which is water, plus the moles of sugar, sucrose, 99.5. Sorry, let me make that prettier. 99.5 divided by 342. So this right here gives you the mole fraction of water. And what is the mole fraction of water? It is 0.983. Is that 366? Yes. So is everyone okay with the mole fraction of water? Okay, and so it's just the vapor pressure then is just going to be the mole fraction, 0.983 times the normal vapor pressure, 23.8. And doing so, you get 23.4. So this is pretty straightforward though, right? So it's the tricky thing is just calculating out the mole fraction, remembering what the mole fraction is. And you can see it's for solutions in the solvent, it's oftentimes quite high, right? And what this means though, with Raoult's law, if you have a solution, so let's say I have a solution, it's just my beaker, and then I start put in stuff in the solution. So it's dissolving, and what happens to the vapor pressure is it actually goes down slightly. And the reason being is because the solvent, so what they have the most of is tied up by the solute. If it's tied up by the solute, it doesn't have the freedom to leave as easily. So that's Raoult's law. And let's see here with that. Now let's say that we were doing this, and instead of sucrose, let's say we had sodium chloride. So if we did this with sodium chloride, we would then, in the mole fraction calculation, we would put a 2 there because sodium chloride dissolves into sodium plus and chloride minus. If we had magnesium chloride, we would put a 3. So, and by I mean when you do the calculation for the solvent, this would be the solute. When you do the calculation for the solute, and it's a colligative property, so that means you have to put the moles of particles. And magnesium chloride, so MgCl2, dissolves into 3 particles. Magnesium plus 2, chloride, and chloride. Turns into 3 particles. So when you do these calculations, you have to put that in there. Does that make sense? Okay, so let's talk a little bit more about Raoult's law. And when you have mixtures of things, so if you have two solvents, say something like, I don't know, alcohol and water. So it's the pressure of the solution is the mole fraction of 1 times the original vapor pressure of 1, and the mole fraction of the other is a mole fraction of the other one times the normal vapor pressure. And if you have a solution with 2 or more, then you just add them up like that. And here are 3 cases. So here's the ideal solution. And this is where the solutions mix and all the vapor pressures add perfectly. So alcohol and water behave very ideally like this. So then there are some cases where the solvent and solute have very strong interactions. So, and you can get a case like this. So when it's a strong interaction, so if you, okay, again, so I guess I should describe the graph. The y-axis is the vapor pressure. So y-axis is the vapor pressure, and indicating this, B is a higher vapor pressure than A. And the x-axis is the mole fraction of A. So right here, we have no A, and then the solution is pure B. And here on the right, we have mole fraction of 1, so 100% A, and the solution's vapor pressure is whatever pure A. And then here at like 50%, it's going to be half of B and half of A. And then you have just the different increments there. So let's say there's a really strong interaction between the solvent and the solute. And these dashed lines show, so this dashed line here shows that where it should be, and the vapor pressure of the solution actually goes down. So what is happening is there's a really particularly strong attraction, stronger than normal attraction between the solvent and the solute. You can have that go down. And if there is a very weak interaction, you can see, well, like that whereas this one goes down, this one pushes up. So you actually have the vapor pressure go up. And you do see this quite a bit. This is also causes a phenomenon called steam distillation. And although this graph assumes infinite miscibility, not everything is infinitely miscible. So, and although things are getting better for if you go eat a fast food, but you ever gone to like a fast food place like McDonald's or Wendy's, or like gone like on the mainland, like one of those like kind of classic truck stops like Waffle House or something like that? And they ever gone in the place and they say it's a greasy joint. You say this is just a greasy truck stop or something like that. And you can literally you can feel, you sit down on the plastic chairs and you're like, this feels greasy. And you like touch the tabletop. This is greasy. What happens is, so oil, like oils, grease, you know, it can dissolve very, very slightly into water. Not very much, but ever so slightly. But if you have just a little bit of water, a little bit of grease and a lot of water, and you heat up the water, it actually will boil. The grease will since, and also grease doesn't like water. It will, I mean, not really. I mean, the grease loves water, like we mentioned in the previous classes, but the water pushes it out. The grease will vaporize at a significantly lower temperature. It'll be slightly at atmospheric pressure. It'll be slightly below 100 degrees Celsius. So it'll be slightly below the boiling point of water. And if you've ever deep fat fried a turkey before, I mean, like you can get oil really hot and it doesn't boil, right? Oil can get really, really hot. And that's amazing that you can get oil to distill, to leave solution at a significantly lower temperature. And this is also steam distillation. This is also how we make fragrances. So things like rose flavoring, or just a lot of things, like just when you get fragrances for things, they take a lot of they take whatever it is they want. In case of for roses, they put rose petals in water. But say you wanted to have like orange blossom or something like that, you know, you throw orange blossoms in water, and then you start to boil that, and then the fragrances, the flavor of whatever you have in there comes out at a slightly less than boiling point of water. So you can really concentrate out those fragrances. So, and that's using steam distillation. So that way you can do that and not have to heat it up to, I don't know, whatever, 500 Fahrenheit, so like a couple hundred Celsius, you know, and if you do that, you might damage the whatever you have in there. So do you ever wonder how they get, like, how that works for fragrances? So how are we doing? Some more questions? So then mentioned about vapor pressure. And the liquid phase is actually kind of elusive. I mean, it's weird for us here on Earth. I mean, because we're so used to water. I mean, we see, I mean, you know, the vast majority, something what, like 70% of the Earth is covered in water. I don't know the exact number, but it's a large amount. But if you study astronomy, you know that having liquids on planets is really kind of weird. And the only other object in the solar system that has significant amount of liquid on the surface is Titan. It's a moon of Saturn, or satellite, I don't know, satellite of the planet Saturn. And it has hydrocarbons on the surface, and the Earth has water. Titan's a really weird planet, or not planet, moon. It'd be fun to go there. It has an atmosphere thicker than the Earth's, but the pressure, the atmospheric pressure is about 1.5 atmospheres, but the gravity is less, so it's actually really thick. And I think if you had like a pair of fake wings, you could like beat your arms and maybe fly on whatever, on Titan. But anyways, liquid phase is actually, like, in terms of states of matter, it's hard to find, and not very common here on Earth, but not very common else in the cosmos. And we have a phase diagram here. So the x-axis is pressure, y-axis is temperature, and this blue line here, this is what it normally would be the phases. And if you have a solution though, what you end up doing is you expand the liquid phase. Liquid phase gets a little bigger. And what's going on, we have, so the change in freezing point is now the M, the molality, times the Kf. What is the Kf? It's the constant for freezing point depression. And then the change in boiling temperature, delta TB, is molality times the Kb, the constant for boiling point. And this is pretty straightforward. And in fact, I even had a question from one of the online students. Student like, I don't understand why I got this question wrong. The most common mistake in these is forgetting to subtract the boiling point and then add the elevated, subtract the melting point, add the boiling point. So it's freezing point, depression, boiling point, elevation. If you can't remember, think freezing point, depression, I'm down, I'm sad, depressed, goes down. And there's boiling point, elevation, I'm high, I'm excited, I'm going up. So remember that. Elevation is up, depression is down. So here are some of the compounds and then their Kf values. So where's water? Water has, believe it or not, has a pretty low one. So 1.86 and 0.51 for boiling. But look at benzene here. It's 5 and 2.5 respectively. And carbon tet, that's really high, almost 30. So, but here's various things, various whatever compounds. And water is pretty easy because in a way the molarity and molality are very close in value. But and part of that is because the density of water is 1. It's just the molality tends to be slightly higher because of the volume. But we have different densities with the organic compounds here. You can get very different answers for molarity and molality. Okay, so let's do this. So freezing point of a 0.17 molal ethylene glycol solution. So it's just the molality. So the freezing point depression is then the molality 1.7 and then times the Kf. I think it's 1.86? Yes. 1.86 degrees Celsius per molal. And if you do that, It is going to be 3.2 degrees Celsius. And like I said, the most common mistake is students go, okay, 3.2, the freezing point is then 3.2 degrees Celsius. Done, move on. No, this is the freezing point, depression. It's depressed. So the freezing point is the normal freezing point, 0 degrees Celsius minus 3.2 degrees Celsius equals negative 3.2 degrees Celsius. So this is the freezing point. And and I mentioned these are colligative properties, and unfortunately, I keep on using examples that have only one particle. So let's say that it was 1.7, say it's 1.7 molal sodium chloride. If it was 1.7 molal sodium chloride, the delta TF is going to be 2, because there's 2 particles times 1.7 times 1.86, which is going to be 6.4 degrees Celsius. So 1.7 molal sodium chloride solution is going to have a freezing point of minus 6.4 degrees Celsius. So, and this is particularly applicable right now, not in Hawaii, but everywhere else. Well, not everywhere else, but there was just a big storm that happened in the Midwest in the United States. And one of the things that you commonly do when it have a snowstorm is you salt the roads. And what does salting the roads do? Well, it melts the snow. It only works to a certain point. When it gets too cold, you can't melt the snow anymore with salt. So actually what they do I used to live in Wisconsin, and when it got to be really cold and they would plow the roads, I mean, plowing works. But then in certain spots, they would put sand down just to give the road a little more traction. So, but definitely put salt down. And when it snows, it usually gets warmer. It doesn't snow as much when it's really, really cold. But when it's warm enough to snow, usually the salt will melt the ice. And what's really bad sometimes though is when it snows and then the sky clears and it gets really cold, and then it gets so cold that it melts all that ice. Now you melted the snow, but now you've got like a half an inch of ice on the roads. So that can be dangerous. So how are we doing so far? Questions? Okay, and so what? We are studying right now, and we've been studying this for a while. And we have 2 applications we're studying hibernation. And we have 2 applications for it. One of them is space travel. We want to be able to hibernate people with space travel. And the other one is obesity. That's one of our things that's one of our issues that we have with our health, at least us large Americans. But, and we look to bears. So some bears hibernate, but other animals, they have different adaptations. So frogs, for instance, frogs, they're also cold-blooded creatures. We're warm-blooded. We always keep our body temperature to a certain level. But other creatures, predominantly, lizards and some amphibians, they are cold-blooded, which means they don't regulate their body temperatures like we do. And as in frogs in certain areas that they get frozen parts, they right before the frog is about to freeze, it'll release a bunch of adrenaline, and then a bunch of glucose goes into its bloodstream, and it has this large amount of glucose acts as an antifreeze. So it causes the fluids in the frog to have a freezing point depression, and then the frog won't freeze, but its metabolism will slow down very, very slowly. And then when the spring melt comes and the frog warms up, it's got lots of energy and hops away. So, and freezing, of course, is important to prevent water from freezing because water is a weird substance, and water also expands. The alpha ice, the common form of ice. Of course, there's other types of ice, but the common form of ice expands then upon freezing. So if you freeze cellular tissues, you can cause it to rupture the cells. So the water expands and the cells can break. So this is one of the adaptations that frogs, certain types of frogs have come around. They'll use the adrenaline and then this freezing point depression to prevent them from freezing. We're looking at bears. So we want to study. We've been studying bears, and because bears they hibernate and like they wake up from their hibernation and they've got lots of muscle mass and bone density. So, right, for humans, if you put us into a coma, and if we're in a coma, in a comatose state for, a couple months, if you wake up and it's going to be hard, you're going to have your bone density is going to be nothing, and you're going to be so weak, you're going to barely be able to lift your arms and stand. Right, it'll be like the humans on Wall-E or something like that. You're just going to have no muscle mass, no bone density. So the bears, they wake up, and they scratch their backs on a bunch of trees and shed all their fur and then go and, eat salmon or whatever they do, whatever bears do in the springtime. I guess it would be fall for the salmon with the salmon run, but I don't know. But I think you get the point. So we want to do that. So because when it comes to interstellar travel or even interplanetary, to get to Mars, say you want to go to Mars, it's going to take at least a half a year. I think it's longer than that. It's probably maybe on the order of a year and a half to get to Mars. Depends on how fast you go, of course, and where Mars is in relation to the Earth. But it can take a long time to get to Mars. And what are you going to do? That's going to be boring. And it's not going to be a big spacecraft either. It's not like you can go and work on art projects or something like that. You probably barely have enough room for a treadmill. So what are you going to do for that whole time? So, or you could say, what, we'll just put you in hibernation. Doesn't matter if it takes you 5 years. You just wake up and build us a Mars colony, kind of thing. So that's one of the things we're looking at. The other thing has to do with fat. So, and we humans, there's two types of fat. There's brown fat and there's white fat. We humans have quite a bit of white fat. We don't have that much brown fat. Whereas infants, actually human babies, they have quite a large amount of brown fat. And brown fat is something that you burn just to stay warm. And other animals have, bears, for instance, have lots of brown fat. And that's what they burn also when they hibernate, is to stay warm. And so we have humans, we don't hibernate, first of all. Secondly, we stay warm by taking the furs of other animals and or our industry. I know, but our industry is only 150-ish years old. And also, fire. So we didn't really need our bodies to provide heat. We can find heat externally. So we kind of lost the ability to, we do have brown fat, but we just don't use it the same way that other animals do. And other animals can turn white fat into brown fat much more quickly. So that's one of the things we're looking at humans is okay, let's find a way to turn white fat into brown fat. And wouldn't that be awesome? Everyone here is skinnier than I am. So let's say I wanted to lose 20 pounds. What if I just, took some drugs that would turn, I don't know, 10% of my white fat into brown fat. And I'm like, you know what? I'm just going to Alaska and I'm going to hang out in my shorts and t-shirt, outside in Fairbanks, for about 2 weeks. And I'll, that'll make me lose, 10, 20 pounds, that'd be awesome, right? So that's one of the things we're looking at, but we're not there yet. Okay, and so here's another drawing, and so we talked about colligative properties. So there's vapor pressure, freezing point depression, boiling point elevation. The last one I mentioned was osmotic pressure. And this here is a tree. This is my PhD in chemistry, artisticness, showing you a tree. And trees are able to, with their root systems, can draw water up into their leaves. And how do you do that? And the answer is osmotic pressure. So osmotic pressure. And so I'm going to do an example. Well, you're going to do an example to show you how it works. But so an atmosphere of water is equal to 33 feet of water. So, or 10 meters, 33 feet. That's the same amount of pressure in an atmosphere of pressure. So if you wonder how can, this leaf here on the top of the tree, I mean, of course it can rain, you can get water that way, but trees can also draw water from the ground. How can that water go from the ground up to that leaf? And the answer is osmotic pressure. And then there's a series of channels that happen in the roots and then also in the trunk of the tree. And it can draw the water all the way up there. And like I said, osmotic pressure. And one of my colleagues, he's a physical geographer. So, and he studies nutrient flows. And one of the things, like, of course, whenever we're at faculty meetings and whatnot, and well, I remember we were on the Big Island and we were walking through the woods and he was talking about the nutrient flows and that kind of stuff. And he's telling me, like, Mike, think of trees as water pumps. So that's all they are. Trees just take water from the ground and they pump it up to their leaves. And I remember that, and I was also watching Planet Earth later. You ever watch that with David Attenborough? It's showing like all the fog and stuff like that the trees were doing. I'm like, oh yeah, that makes sense, because trees are water pumps, duh, I know. But how are they water pumps? Osmotic pressure, specifically. And here's what we mean by osmotic pressure. And this is a very specialized piece of equipment. This is called a U-tube apparatus. So because it's a tube in the shape of a U, the letter U, and if you put a semi-permeable membrane in here, a semi-permeable membrane is something that will allow water to pass through it, but bigger molecules it won't let pass through. And we used to do this, so we do this in a different way now, but we would, if we wanted to figure out the molecular weight of a protein, and proteins are huge molecules. If you put a little, say I wanted to figure out what the molecular weight of the spike on the COVID-19 protein is, I could, take a bunch of spikes and toss them in there and then wait. And then what would happen is the water would preferentially go here. And then there would be a difference in the height of the U-tube apparatus. And then this would, of course, be, well, if you remember then the 10 meters equals 33 feet equals an atmosphere. From the height of the water difference, you can then determine what we call the osmotic pressure of the solution. And that's where the osmotic pressure, like I said, where it comes from. We don't do that anymore. So nowadays, if we want to find the molecular weight of something, we go and well, what we used to do, maybe I'm showing how things have changed in the past 5 years. We used to take the protein and we'd throw it in something called an electrospray. We kind of charge it and throw it into a vacuum chamber. And then we'd just hit it with electricity and then by time of flight. So if we charge it by -1 and we put it in a positive plate at a kilovolt of potential, we'd see how long it takes to fly to hit a detector. And because of, the mass with the charge will give you the momentum. And then if you know the time from that, you can backtrack and figure out the momentum. And the momentum is just, it's the mass times the velocity. So you know the velocity by the time, so then you know the mass. That's how we used to do it 5 years ago. Now we just shine everything with X-rays. So and that's what they did for COVID-19, is they took it and they just hit it with synchrotron radiation, the X-rays from a synchrotron, and they figured out the exact location and structure of the protein. So down to the atomic level. That's crazy. It's amazing how things have changed. But this is how we used to do it, like in the 1960s. And osmotic pressure, what we use is the Greek letter, the uppercase Greek letter pi, and pi equals M molarity, R gas law constant, T temperature. So our osmotic pressure is that, and you might notice that's kind of like the ideal gas law, PV equals nRT. So imagine if we divide PV equals nRT, and we divide both sides by volume, and we get pressure equals N over V, so number of moles over volume times RT, and the number of moles over volume is molarity. So it's really just the ideal gas law, just rearranged. So you gotta be careful though, because capital pi and capital pi can also mean geometric series. So if you, it depends on which class you are, I should say subject. And that's one problem, that a lot of times different branches of science and just different branches of just, academia, our symbols mean different things. So for a pure mathematical class, capital pi means geometric series. So you've probably seen capital sigma, like the sum of 1 to 10 of n is going to be 1 plus 2 plus 3 on, and so on. If you have the geometric series pi, if like we had a mathematician in this class, is anyone here a mathematician? No mathematicians. If you have a mathematician and you say, oh, what's the capital pi? You're like, the geometric series? Well, what are your bounds? So this is what they mean. So just be careful on the context. But the context for chemistry is pi is the osmotic pressure. So let's do this. Osmotic pressure of a solution containing 0.587 milligrams of an unknown protein per 10 milliliter solution is 2.45 torr. Find the molar mass of the unknown protein. And so a couple of things here I wanted to rearrange. So M is moles per liter, and moles you can write as grams divided by molecular weights. So, and grams divided by molecular weights. And so if you then rearrange the solution, so rearrange the osmotic pressure equation, you can then solve for molecular weight, where you have molecular weight is equal to grams per liter times the gas law constant times the temperature divided by the osmotic pressure. So, and then, so a couple of things. The R value, we have two different types, right? We have the units. I mean, there's various values of R. There's 0.08206 liter atmosphere mole Kelvin, or 8.314 joules per mole Kelvin. This one, we're going to use the 0.08206 because of the atmosphere as a pressure. We're going to use R quite a bit in this class, but we're going to use the 8.314. So let me solve for molecular weight. And so it's going to be grams per liter. So it'll be 0.00587. That's 5.87 milligrams. Grams per liter, 0.100, it's 10 milliliters, times R, 0.08206. I'm running out of space here. liter atmospheres over mole Kelvin. Temperature is 25 degrees is 298 Kelvin, all over osmotic pressure, which is 2.45 torr, but then it's going to be an atmosphere to 760 torr. So let's look at the units. So torrs cancel, atmospheres cancel, kelvins cancel, and liters cancel. So that means our dimensionality is going to be grams per mole. And then we just have to put in the numbers. And if you do that, you get 4450 grams per mole. So that's a big number, right? 4,450 grams per mole. You know, water is 18 grams per mole. If you did something like gasoline's, I think it's 118 octane, right? So like, man, that was hard calculating that. Can you imagine if it was 4,000? Oh, proteins are big molecules. So this is actually kind of a small protein. So this might actually be something like the spike of COVID. So it's about that big. But this one here, this is more just rearranging the equation and then putting the numbers. Actually, I hope you can kind of see that these, in my opinion, these are actually kind of easy because they're pretty straightforward. Well, at least next chapter, in my opinion, is the hardest chapter in the book. So as a preview for Monday, hit with a tough class. But we'll recap for this one. I will do a recap. And if you want, if my new students, when I do a recap, if you study teaching theory, the teacher's job is to communicate effectively, and the student's job is to learn. And also, with teaching theory, I can't tell you how to make the connections in your mind. That's something you have to do yourself. But what a lot of times I do, I try my best to try and as much as I can to communicate where they're connected. And one of the ways I do is like, okay, I'll teach you something. I'll kind of give you a recap to try and, because you, the student, are the one that have to lay the foundation to how it's all connected in your brain. But I think although it's the student's job is kind of supposed to be more like comfortable. I mean, it's more comforting to some people. Like, oh, it's not my fault. The student just didn't make the connections. You know, but I think that we instructors can help make connections. That's one of my attempts, at least. So we have osmotic pressure. So we had a YouTube apparatus. We threw in some protein in there quite passively, perhaps a tip of a coronavirus or something. And we noticed that the osmotic pressure, the solution had a change in height, which corresponded to an osmotic pressure of 2.45 torr. We had 5.87 milligrams of the unknown protein dissolved in 10 milliliters of solution. So what is the molar mass of this protein? Of course, we would just, like I said, this day and age, we just take it and throw it and hit it with x-rays, but we're not doing that. I guess we're old school. Anyway, so we have pi osmotic pressure equals molarity, moles per liter, times gas law constant times temperature. Molarity is also moles per liter, and a mole is the gram divided by a molecular weight. So we can rewrite osmotic pressure as being osmotic pressure equals the mass of the substance divided by its molecular weight divided by the liters of solution times the gas law constant R times the temperature. We solve then for molecular weights, and we find that molecular weight equals the mass of the substance divided by the liter of solution that substance is times the gas law constant times the temperature divided by the osmotic pressure. So then we put in the numbers and have the right units and make sure we have the right unit conversions, and we get 4,450 grams per mole. So any questions on this, on the math at all? Okay. So what is the osmotic pressure of a solution that has 1.5 grams of ethylene glycol in 50 milliliters of water at 298 Kelvin? Osmotic pressure equals MRT. R is given, ethylene glycol is 62 grams per mole. Oh, why the heck did that go down? When did that go down? Oh. Oh, I'm sorry. You should have told me. But that's what I mean. It's it's not your fault. No, it's just, hey, that happens again. Just hey, like, hey. Remember, my job is also to communicate effectively and clearly. So it would help my job if you were to tell me that. Ethylene glycol. Ethylene glycol. Yeah. Some people think it's A, B, C, D. Okay, yes. Almost everyone's going for C, and that is the correct answer. So, and there's the math there. It's just a matter of putting in a calculator correctly. But 11.8, so this is the osmotic pressure, 11.8 and 11.8 times 33 feet. This then corresponds to 389.4 feet of water. So 400 feet. So that means if you have like if instead of sugar or something like that, it's ethylene glycol. You know, if I had a long tube and I had, you know, a little bit of solution and I connected a tube of water, so I had this solution and I had like a tube full of water, I could draw water up, so 390-ish feet, almost 400 feet, you know, against gravity to that solution. So that's how trees can do this. And so they have in their leaves and in various places, they have very sugary sap. And that very sugary sap has the ability to draw water, several hundred feet from where it's at to the plant wants it to be in the leaves to photosynthesize. So that's how it's able to do it. I think it's awesome. That's amazing. 400 feet and 1.5 grams and 50 milliliters of water. That's nothing, And I mean, I guess so for sugar, let's see here, sugar is going to be 180 grams from also 3 times that. That'll be less than 5 grams of sugar. So if you put less than 5 grams of sugar and 50 milliliters of water, I mean, that's pretty sweet. That's not that sweet. It's not like rock candy sweet. That could draw water up 400 feet. That's nuts. So, all right. I am not going to test you on this, but I want you to know there's something called the Van Hoff factor. So the Van Hoff factor, so here you have in solution. So in solution, this is where you'd like it to be. You'd like there to be, so here's sodium and chloride dissolved in water, and you'd think that they behave like 2 particles. But sometimes though, the ions can pair into solution, and instead of having 2 particles like here, this is clearly 1, this is clearly 2, when they pair together, it looks like they have just 1. And the problem with this is for colligative properties deal with the number of particles. And so you would expect there to be a certain number of particles, but we actually observe it like it's less. So for instance, sodium chloride, you expect there to be 2 particles, but we find out that it really behaves more like 1.9 particles. And magnesium sulfate, you think it should be 2, but it really behaves like 1.3, and so on. So for these various different types of ions. And this just messes things up. So what I do though is I don't include Van Hoff factors. So in this class, we only deal with ideal solutions. But if you have future classes that talks about Van Hoff factors, and there's another thing, there's something called an activity coefficient. That's the chemistry's way of multiplying the answer. Like it's like if you do the problems properly and then you get the wrong answer, so you multiply your answer by a certain factor, you get the answer in the back of the book. It's like that's like we'll call it the Ferguson factor or something like that. That's just the factor you add to get the right answer. That's what an activity coefficient is. So Van Hoff is like this too, and you might see this in other classes. I wanted to mention it, but I'm not going to test you on it. Everything is ideal. Okay, this I will test you on, something like this. Which solution will have the highest boiling points? So half molar sucrose, half molar sodium chloride, or half molar magnesium chloride. So remember, solution, the delta TB is the molality times the KB. This is all aqueous, so the KB is all the same. And although we have moles and molal are closely related. And if you look at this, so sucrose, this is a molecule, this is going to be 1 particle. Sodium chloride, it's going to be sodium ions and chloride ions, it's going to be 2 particles. And magnesium chloride, it's going to be magnesium plus 2, Cl minus Cl minus. This is going to be 3 particles. And the colligative property is the number of particles. So the sucrose is going to have a big old 1 here in front of that. The sodium chloride is going to have a 2 in front of it. Magnesium chloride is going to have a 3 in front of it. The one with the highest magnitude is, in fact, the magnesium chloride. That's the one. The one that has the highest boiling point is going to be the magnesium chloride. Does that logic make sense? Highest number of particles. So this one has, so A has 1 particle, B has 2, C has 3. I feel like I guess I'm not doing the count voice. Because it's water. Yeah. It's implied because it's water. These constants are just different for the solution. For the solvents. Yeah, if you go, I went too far. So the solvents here. So here are the freezing point, depression, boiling point, elevation constants for liquid solutions, liquid solvents, and water. It's right there. And it's implied, I mean, it wasn't explicitly said in the problem. It was implied it was water. Almost always, yeah. Because I mean, here on Earth, right, we have the oceans. Most of the planet's surface is an aqueous solution. And for biological things, I mean, chemistry and biology are very related. Usually when you talk about solutions, you almost always mean aqueous. Yes, there's other solutions. Usually you mean liquid aqueous solutions. Yes, I know 14 karat gold is a solution. It's a solid solution, but most people think solutions, it's water solutions. Other questions? And if something happens, you can always ask. The tests, I don't have a time limit. So worst case scenario, and there's something that's really confusing, you can just make a note of it and then drop me an email later. Okay. And now I am not going to test you on the next sets of topics I'm going to talk about. And unfortunately, I had actually hoped that I was going to be able to teach from home. I think I enjoy, my energy level is actually higher now. I hate teaching on Zoom, but I was hopefully going to show you some colloids because my wife she bought some sort of dessert thing from China, and it's a colloid, and I thought I could show it to you. And also, there's certain beverages are also colloids. Absinthe, for instance, is a colloid. But you can have mixtures of things that are colloidal dispersions, and I'll jump ahead and tell you a colloid. What makes a colloid is something called the Tyndall effect. The Tyndall effect is the scattering of light. So if you see this, you have a flashlight here and 2 solutions. Which one is a colloid? The one on the left is a colloid because it scatters the light. And sometimes you can see sunbeams. You can't see sunbeams. You can't, you're seeing light that's being scattered. It's dust. So if you're in somewhere like an old dusty building, or if it's kind of a dusty day, if there's a lot of particulates in the air, you can kind of see sunbeams, coming down through the clouds. What you're seeing is the scattering of light. That's called the Tyndall effect. But here are different types of colloidal dispersions. So these are not solutions, but they're kind of they're a meta-stable. So meta means sorta stable-ish solution-like thing, but not really a solution because it's not homogeneous. So it's solution means homogeneous. So we can have an aerosol. An aerosol is when you have a liquid dispersed into a vapor. And an example that is fog. So fog is water droplets in air. And also similar to fog, you can have smoke. So, well, solid aerosols, where you smoke is a solid aerosol. And I told you with the Tyndall effect, like I remember when I would go camping and if the fire was especially smoky, sometimes I'd even throw leaves on the fire just to make it smoky. And my friends and I would take flashlights and pretend they were lightsabers, like from Star Wars, and then we'd, kind of, I mean, of course, they don't stop because they're not actual the whatever lightsabers, but we could pretend that they were lightsabers and we'd pretend fight, that kind of thing. But that's the Tyndall effect, and that's also the solid aerosol. Foam is when you have a gas dispersed in a liquid, and whipped cream. Whipped cream is an example of foam. And if you've ever actually made whipped cream, I made it once by hand, and I will never do it again because I always get it only happened once. I got cramps in my forearms because I had a whisk and I had some whipping cream. I'm like whipping the cream, like, man, it's taking forever, and after 5 minutes of it, my arms are burning and I have like a little bit of whipped cream. I'm like, ah. Or you can just take like an egg beater, like an automatic one, and just what I do now is if I want to make my own whipped cream, I'll get a big mixing bowl and I'll get one of the automatic electric egg beaters, and I actually cover it because I whip it around. I whip a lot of air into it, so it splatters all over, and it makes my hand full of cream. But then it whips a lot of air into it. It only takes a couple of minutes, but it's a lot easier than doing it by hand. What you do with whipping cream is you whip gas into the cream. You can also have two liquids. You can have liquid emulsion. And so certain beverages like milk. Milk is fat dissolved into liquid water. And how do you get that all talk? It's used as a similar principle to soap. So a soap is you have a surfactant molecule, usually negatively charged in most soaps, and the oil dissolves into the oil. The nonpolar part is okay with this end, and then the ionic part on the outside is favored by water, so you can get the whole fat droplet suspended into something called a micelle. And that's also how you wash your hands. So if you're like I don't know, cooking a turkey or cutting up a turkey and your hands are all greasy, and what do? Like, well, if you wipe it on a paper towel, your hands are still you got that thin film of grease on it. Oh no, use soap. And I put water and soap in my hands, and what do? Then you rub your hands together. So rubbing your hands together does something. What you're doing is you're mechanically forming the micelles. And the micelles, they're these structures that have the ionic heads on the end, and then the tails, the nonpolar tails around the oil droplet. And then you can then the whole thing washes away. So that's how you can have two different immiscible liquids and form an emulsion. For milk, it actually, the emulsifier, so most fats are triglycerides, which means we have glycerin and then we have the fats attached to them. So I drew it kind of, if you look at it in textbooks, they'll have them three like that, but truth of the matter is they'll be spread out, in three different directions. If you remove one or two of those tails, you get a non-ionic surfactant, and you can dissolve some fats in that. So that's how milk works. So at least as far as and these are then this is glycerin, so then this becomes OHs. So then this is the tail that the water likes, and then this is the tail that the fat likes, and you form a micelle, and that's how you can get fat to dissolve into water, like for milk. And so not listed here, you can have something, actually no, I guess you can have solid emulsion. It's also, although we give it kind of its own state, Now let me think here. You can have another one. I'll add a new line. You can have a solid and a liquid, and we can call this a hydrogel. So we use hydrogels for various things. Jello is a hydrogel where you can have a solid. And if you ever made Jello before, you have a little bit of powder. Well, it's not a little bit. I guess it's a moderate amount, but you put a lot more water in it than you do for Jello. You put, like I said, there's more water, so it's more of a solvent. Water like a solvent, and you have the powder, and it forms this, kind of wobbly solid kind of thing. That's also known as a hydrogel. And the most common thing we use, I guess my shut up alarm. We use it for contact lenses. All right, I'm done with things. And I already said to null effect. Okay, my shut up alarm has gone off. It's time for me to shut up.